Alright, in this video we're going to talk a little bit about probably in some ways the most important branch of chemistry that applies to outside life that you'll ever see, and that is chemistry of polymers. Now the only reason that's important is because the fact that polymers are so widespread throughout, oh boy, everything that we do. I can guarantee there is nothing you can do where you don't interact with polymers at some point, whether it's driving, whether it's eating, whether it's going to the bathroom, whether it's cooking, whether it's sleeping, whether it's who knows what, watching TV, handling a DVD, everything, reading a book, everything is to do with polymers. When you wrap your food in what we call cling film or sarin wrap or whatever the hell you call it, that's a polymer. Now, one of the most important polymers, at least historically, is this guy, nylon. Now, you guys know what nylon's used for. It's used for actually a whole host of different things, but one of the things it's used for is stockings. In fact, that was what it was first used for. A chemist by the name of, I think his name was Wallace Carruthers, was a guy that discovered how to make nylon. Would have become extremely wealthy over it if he hadn't committed suicide before it became really, really popular. Unfortunate guy. Anyway, so we're going to talk about several different examples of polymers. Nylon, which is essentially a polyamide, and we'll talk about that down here. Polyesters, as you can imagine, a polyester means a polymer that's lots of ester groups linked together. These names, by the way, in brackets, these are just trade names that these polymers are manufactured under. So whenever you see the term Kevlar, you guys will know what Kevlar is used for. You've heard it before. That is a particular polymer, but it's not traded under its normal name because that would just be too long and boring and difficult to spell out. So they use the word Kevlar because it rolls off the tongue better. All right. And so nylons, polyesters, polycarbonates, and then we'll talk a tiny little bit about one other interesting up-and-coming feature of polymers, or biodegradable polymers, those that degrade in the environment, or in the case of sutures that degrade in your mouth or somewhere in your body when you have some stitches put in. I imagine you've all at some point had some stitches put in that they call dissolvable stitches. I know I've had them when I had surgery inside my mouth, that sort of thing. Rather than having to take those out later on in a very painful process, they just put sutures in that they know will dissolve over time by the acids in your mouth. It's a very useful thing to be able to talk about. Anyway, let's start off by talking about nylon. Now, just before we do that, though, we should talk a little bit about what this means. Step growth. Step growth means they grow one step at a time. Two molecules add together, another molecule adds on one end, another molecule adds on another end, another molecule adds on, so on and so on and so on, until your molecule just gets huge. So you guys have seen what the reaction between an acid chloride and an amide looks like. Yeah. An amine, sorry. You get an amide. Now that's something that you've seen before, that's not really a surprise, but what about when we have something like what we have shown on this page here? We have not just an amine, but a diamine, and not just an acid chloride, but a diacid chloride. So if these two were to react, and you can actually do this very easily in the lab or in class as a demo, and assuming we have the right chemicals, I can show you guys this because it's really neat. The mechanism that happens is exactly the same to what you've already seen. All right, the electrons from the nitrogen go into the carbonyl, the electrons kick up onto the oxygen, then they kick back down. I'm showing more steps, more than one step here, all on one. just because I can't be bothered to write the whole thing out. But what you end up with is the leaving group coming off. And what's of particular relevance here is you now have this, and let's count our carbons here to make sure that we're doing this right. 1, 2, 3, 4, 5, and 6. And let's count the carbons in the amine too. 1, 2, 3, 4, 5, and 7. Alright. Not really 7. So, if I just draw out my carbons here, then what I've done overall is, there's my carbonyl group, because I've kicked out the chlorine. And I've bonded that to my nitrogen. Let's see, 1, 2, 3, 4, 5, 6. Then we have our nitrogen, and then carbon 1, 2, 3, 4, 5, 6. Then the other NH2 here. All right. So the way this, oh crap! You see what I've done? See how I've messed that up? Sorry, everybody. That was my fault. My apologies. We were supposed to be making an amide, and I didn't do that. What a dumbass. Okay, hang on. That's a good way to start things off. That's what you get from making videos at 12:55 in the effing morning. Anyway, so let's put all our atoms on. 1, 2, 3, 4, 5, 6, and then we have our NH2 here. So what we've made is an amide right here. Now the idea behind a polymerization like this is there are plenty more molecules of this and plenty more molecules of this. So the first step essentially is these two molecules reacting together to form this. And then in a second step, because we still have an acid chloride here, another of these molecules can just add on to this end. Or, if you wanted, another molecule of this could add on to this end. And the same thing happens. So what you can see is this molecule just gets bigger by 6 carbons on this side, bigger by 6 carbons on this side, and so on and so on and so on and so on until you get to this huge polymer. Any ideas where the name 6,6 comes from? Nothing to do with the devil. 6,6 in this case just means 6 carbons from the diacid chloride, 6 carbons from the diamine. Alright, so 6 carbons here, 6 carbons here. So essentially your polymer builds up with the units of 6 carbons. Alright, so this just keeps going and going and going. And you can literally take a beaker, and if we have the chemicals, like I said, I can do this as a demo, it's really neat. And you have 2 phases in this mixture. The bottom phase is your aqueous phase, which I think contains your diamine. And then the top phase is your organic phase, which contains the diacid chloride. And right at this phase boundary, where the 2 chemicals meet, because this is so reactive, you don't need to apply any heat or anything, they'll just start to react. And if you take a glass rod or something and stick it down in here, push a tiny little bit of the top layer down into the bottom layer, and then pull the glass rod up, you'll actually pull up a string of nylon with you. And then if you just rest the glass rod on top and twist it, you'll keep on pulling polymer out of the solution. And you'll be able to keep on doing that until one of your reagents runs out. If you check out YouTube and look up polymer form or nylon formation, you'll find all sorts of videos about this. But I'm hoping that we can do something about this in lab or in class, because it's a really neat demo. Anyway, that's a little bit about nylon. So I hope you understand what I mean by step growth. Step 1 here, step 2 is addition of this or this, and then step 3 and step 4, addition of 6 carbons each time until your polymer just gets huge. So, and Kevlar is just another example of a polyamide. Actually, question 1622, we can probably talk about that in class, deals with the structure of Kevlar. It's similar to this, except the diamine you start with is different, as is the diacyl chloride. In fact, for Kevlar, it's a dicarboxylic acid, because carboxylic acids are less reactive than acid chloride. You have to heat that up to get it to go, but you'll get a similar reaction. All right, let's move on to polyesters. Now, to make a polyester, or in this case to make this particular polyester that we're going to be talking about, it looks a little odd because it looks like you're already starting from an ester, and you are, except this isn't a polyester, this is just one molecule. What you're essentially doing is linking molecules of this together in a big long chain. Now you can't just throw two of these together and hope them to link up. You need some way to join them together. And that's what the ethylene glycol does here. So if you take these two and heat them up, we have no acid chlorides here. These are not quite as reactive at normal temperature. If you heat these two together, what you'll find is they undergo a reaction where they combine together. And what essentially happens is, on each side of this dimethyl terephthalate, and you don't need to remember the name here, these OCH3 groups come off and are replaced by ethylene glycol groups. So what you end up with, and let me see if I can draw this out, is something that looks like this. Now, polymers look a little odd if you try and draw them out, but I'm going to try and do this. So I'm going to try and draw out the ethylene glycol. Essentially, you can imagine the ethylene glycol is kind of acting as a nucleophile, attacking this carbonyl carbon. You lose this hydrogen in the process. So if this oxygen has attacked this carbonyl carbon, we will get a bond that looks something like this. Alright, there's my carbonyl, and we go to our benzene ring here. Alright. Then we have our other carbonyl carbon here on the other side, connected to another oxygen from another ethylene glycol molecule. Now, what you'll see here, the way most polymers are shown, is essentially a repeating unit of the same thing over and over and over again. Now, because I don't really have the time or the patience to draw this thing out 35 times, plus it'd be a hell of a boring video to watch, the way these polymers are usually represented is by saying, okay, this is the repeating unit, all this, and I'm showing it's repeating simply by putting a bracket, a pair of brackets around it, and saying it's repeating n number of times. And n essentially is however long the polymer chain then ends up being. You can never really control what n is other than a very large number. And then the OCH3 and the hydrogen from the ethylene glycol would combine to form ethanol byproduct. All right. But this is the structure of polyester that's known as Dacron or Mylar. So it's exactly the same compound in each case, interestingly enough, but it's given under two different trade names depending on what it's used for, as weird as that sounds. Dacron is a polyester used to make clothes. You guys have seen labels on clothes where it says X% polyester. Well, that's what that is. That's this, most commonly this polyester. And exactly the same molecule extruded in a different way is called Mylar when it's used to make recording tape, which may not be used that much anymore, but that's what it's used for. The funny thing about this is this stuff, although it doesn't look it, this is about as strong as steel when it's spun out to fibers. Crazy when you think about it, but that says a lot about the strength of these bonds. So that's an example of what we could call polyester. Another example of a polymer here is called a polycarbonate. All right. And this is kind of similar to what we saw in the previous video, in the previous slide. We take these two molecules, and in this case here, pH just means phenyl, I'm frankly was too lazy to draw out phenyl groups like I did here, so pH just means phenyl. All we're doing here is finding a way to provide repeating links between these two to make this big polymer. Essentially, you're linking molecules of bisphenol A together via this diphenyl carbonate. Again, we have no acid chlorides here. They're not particularly reactive at room temperature, so you've got to heat the hell out of them to get them to go. So the polymer that we get in this case looks something like this. And just as I did on the previous slide, I'm going to have a pair of brackets around the repeating unit at the end. Simply because, like I said before, I don't want to draw it out 500 times. And you know what? I realized I'm screwing this up already. I color-coded my OH groups just so you could follow what I was doing, and of course I'm messing it all up. So let me start again in black. So what we have is the benzene here, and the reactive part of the bisphenol A here is not this benzene stuff in the middle, but the alcohol groups on either side. So I'm just drawing these out. Alright, and okay, they look kind of crappy, but oh well. And this is kind of similar to what we saw before. The alcohol acts as a nucleophile in each case and attacks this carbonyl group, all right, kicking the electrons up and then kicking them back down and kicking off this, essentially kicking off this PHO as a leaving group. So what that provides is a carbonyl group here. Hang on, let me make that black here. What we end up with, that should be an oxygen, not something funky, so that's an oxygen. And what we get is this repeating unit with my red carbonyl group. Alright. So initially what you end up with is something that looks like this. This isn't the structure of the polymer yet, but I just want to show you where we go in here. After these two react, at least initially, we get this. So we've lost one of these PHO groups, and then the idea is that another one of these guys comes in, attacks here, and kicks off this. So what that provides overall is a way to provide a repeating link between the bisphenol A and the diphenyl carbonate groups, which means the overall structure for the polymer looks something like this. Again, we have our N power here, which says, you know, however many units that is. And then we have the PHO groups, the phenoxides, that match up with the hydrogen that came off here, and we get phenol, right, as another byproduct. But this is just another example of a polymer. This is a polycarbonate called Lexan, used for several different things. And so, yeah, the very last thing I wanted to talk about then was simply about biodegradable polymers. I don't really want to go too much into it. The book talks a little bit about, on, funnily enough, page 666, and we'll mention this in class a little bit. Different acids, actually acids that all have alcohols involved. The book talks about glycolic acid, lactic acid, and hydroxybutyric acid, and how you can polymerize those to get biodegradable polymers, but we'll mention those a little bit in class. It's due at 1 o'clock, and as Han Solo said in Star Wars, shit, what did he say? No, that wasn't what Han Solo said. I was just trying to remember. You're all clear, kid. Now let's blow this thing and go home. Now he said it with a little bit more vigor, but he wasn't doing it at 1:08 a.m. So it's good night from me, and it's good night from him and her and Yeah, bye.